To finish off for the day, we're very happy to have Carlos Amendola, and he's going to tell us about linking invariant theory to maximum likelihood estimation.
Thank you very much. I want to thank the organizers for inviting me to give a talk in this workshop. I'm very happy to, and I'm happy to talk to people in different communities and bringing this message of, I guess, algebraic statistics and how there are some nice, very cool tools and theory that you can develop in algebra and geometry, and it relates to applications in statistics as well. And there's this back and forth. So let me get into it. So the context is really this algebraic statistics, where we have these methods from algebra and geometry to apply to problems in probability and statistics. And as I write here, this is a feedback loop. So then you find new questions in probability and statistics that turn out to be interesting questions in algebra and geometry. And so this produces new insights both ways. And this is kind of like the philosophy and essence in here in algebraic statistics. Okay, so I'm going to start with, well, what is a statistical model? So no, I don't assume that everybody knows what it is, but so the definition is simple. It's just a set of probability distributions. And what we actually exploit in algebraic statistics is that most of these models can be described by polynomial equations and polynomial inequalities, right? So that's where the algebra and geometry come in. In the discrete case, how can we talk about such a model? Well, a discrete, you have only finitely many states, let's say M. Then to completely determine a probability distribution on these M states, the only thing that you need is to specify the probability that each state happens, right? So this can be coded in a vector P that is all non-negative entries that sum up to 1. Okay? So this is a subset of the probability simplex, A minus 1 dimensional probability simplex. Okay? And so a discrete statistical model for us is going to be just a subset here. And well, ideally, this subset can be described by polynomial equalities and inequalities. And so, first example I would like to give you is this binomial distribution, which means you flip a coin twice and you record the number of heads. And so there could be either 0 heads, 1 head, or 2 heads observed. And the probability for each of these states is going to be 1 minus theta squared, 2 theta, 1 minus theta, and theta squared, depending on the probability of heads. That's this theta between 0 and 1. And so this is a parameterization of the model that lives inside this two-dimensional probability simplex. And, well, this is a curve, and it can be described algebraically. And so this is defined by the Hardy-Weinberg equation, which is this important equation that appears in population genetics, which says that 4 times P0 coordinate times the P2 coordinate equals the second coordinate squared, as you can verify from the parameterization. Okay, so this would be an example. And we can see this geometrically. So here you can see the picture of the probability simplex. And here in red is the Hardy-Weinberg curve, which would be the model. Okay, so this would be the first example. Okay. Any questions so far? Great. So another important example is independence model. So let's say you have 2 variables, x and y. X has possible state space 1 to r. Y has possible state space 1 to c. And then the question is, are they independent? Right? So independent means, well, that the probability that at the same time x equals I and y equals j, this can be written as the product of the 2 marginal distributions. Okay? So, well, for example, if let's say you have a 2 by 2, so two binary random variables, well then this joint probability matrix can be written as this outer product of the 2 marginal distributions. And here I'm using this notation with the pluses, which means that whenever you see a plus, you sum all the possible values that this plus can have. Right? So here in example, P1 plus is P11 plus P12, and P plus 2 is P12 plus P22, and etc. Then you have this nice factorization. So the independence model is simply all joint densities, joint matrices, such that you can write them in this way. And of course, you can see that this will be, well, so this means that this is actually an algebraic variety in the sense I was talking before, being by polynomial equations. These will be polynomial equations that hold. So this notation VF. But another way of saying this is simply these are rank 1 matrices. Right? So these are rank 1 matrices that can be written like this. And so you can have algebraic equations given by these 2 by 2 minors of P. And you can think that this is easy to generalize to any number of random variables. And in that case, we would get a tensor. And then the condition is that then the probability tensor will have rank 1. So then that would be another product of as many components in terms of the marginals. Okay? So again, this is everything very algebraic, and it has very deep, important meaning as independence. It's very important in probability. All right, so this is an example of the 2 by 2. This surface. I have 2 pictures, so this one here, and then this other one. And there are some, I don't have one with me, but there are nice some 3D models that have been printed. All right, so now my talk says something about maximum likelihood estimation. So what is that about? Well, the goal is of given data, so you observe data, and you have a model in mind, then you want to find the point in the model that best explains this data. Okay, so that's the goal. And in this discrete case, the data actually can be summarized in a vector of count. What does this mean? So when you're observing these heads and tails, the only thing that matters is, this is basically because of in the way the sample is drawn, everything is independent. Then it only counts how many times you observed each state. So for this coin example, it only matters how many times you observe, how many times you observe heads, how many times you observe tails. It doesn't matter the particular sequence that you actually observe. Okay, so these are these UIs, and this is this vector of counts. And from there, one could have an empirical distribution, which is just normalizing by the sample size. This n, which is the sample size, you see it will be u plus in our notation. So I do 1 over nu, and then this will lie in the simplex. Of course, the problem is that this empirical distribution almost surely will not be part of our model, right? Because it's just a random point in the simplex, and our model is usually lower dimension. Okay? So what do we do? Well, the likelihood function is defined like this, and you should think about it in this way. So if we knew p, then this would be the probability of observing these particular counts u1 to um up to a multiple, and so because everything is independent, right? So if I observe u1, so I observe u1 times, then I would get p1 to the u1, right? And everything multiplies until this one. So really the point here is, well, if we knew p, this gives us some likelihood of observing this particular u. But we don't know p, that's what we're trying to estimate. We know u, so the MLE, so-called MLE, maximum likelihood estimate, will be the maximizer of this function over the model. So you go over your model and try to find the p that best explains the data in this sense, that makes the data most likely. Okay, so this is the crucial definition. And let me give you the example for the binomial. So let's say we do this experiment of flipping the coin twice, many times, and then I record how many times I observed 0 heads, how many times I observed 1, and how many times I observed 2. And the question is, well, now with this information, what is your best guess of the original probability theta? Okay. And it's not hard to see that the maximizer is given by this rational expression, rational expression in the u's, which is u1 plus 2u2 divided by 2 times this. And this is very intuitive because if you think about it, u1 plus 2u2 is the total number of heads that you observed in this sample, right? So you observe u1 every time you observe 1, and then 2 times u2 whenever you observe u2. And then this is the total number of heads, and this is the total number of throws, right? So you do u0 plus u1 plus u2, and since every time you're doing the experiment twice, it gets multiplied by 2. And so this would be like the classical frequentist approach would give you this estimate as well. Okay, so a warning is that in this case, everything was very nice, very explicit, but the MLE may not always exist. And this is a big question in general. So this likelihood function may have maybe multiple maxima, global maximizers, or maybe it doesn't even have a maximizer. Maybe it's unbounded. And then you actually never obtain a maximum. So these kind of things can happen. Right? So this M doesn't need to be closed, in principle. Right? So it could be an open, and then it's unbounded. And so, okay, so this is one of the big questions in general. How can you detect whether my MLE is going to exist or not? And invariant theory is going to help us with that. So we're going to go towards that. But first, let me talk about this example. The independence model is a special case of what we call a discrete exponential family, which are very nice models in statistics that have some specific parameterization. In this case, you can think of the parameterization as being monomial, really. So the probabilities can be expressed in terms of monomials. And these correspond to the class of so-called log linear models. Why? Because, so these are all the distributions such that when you take the logarithm, coordinate-wise, they belong to some concrete linear space. And this will be the row span of some matrix A that encodes the model. And these A are precisely these Aij entries that appear here are these A. So you can...
Don't you also need some coefficient in front of the product? For instance, you won't get the Hardy-Weinberg curve without a 2 on one of them.
That is a very good point from Frank. In general, yes, I do need to have some coefficients here. Yes. So then I would not call this log linear, but I would call this log affine model. So I can translate the linear space. Yeah. And yes, okay. And then the beautiful part is that okay, once you have these matrices, there's a lot of geometry. In particular, there's geometry to toric varieties, and so then such a matrix here corresponds to this 2x2 independence model example that I was giving. And okay, then one can study many things, including ML degree, which is one of my favorite topics, but I will not talk about that today. So let's talk about the new perspective with invariant theory. And so this is was introduced. So this is mostly based on so this first paper, John worked with Kathlén Kohn, Philipp Reichenbach, and Anna Seigal here. So this is the title, and what we were thinking about is okay, how to really translate this problem that we just talked about. You have your simplex, you have your model, which is this curve, you have your data point, and you want to find the best point here, in this case the MLE. So on the other hand, there is invariant theory, and there is something about, okay, there's a point, there is some group action, there is an orbit, and you're trying to minimize maybe the norm to the origin, so the norm of this in this orbit, and this would be the capacity problem. So okay, I think many people here are familiar with that problem, but maybe also define these notions of stability. So okay, so you have a vector v, you have the orbit, just you take the set of all the acting by a group G, you take this G dot B, that would be the orbit of V, and then we have these 4 definitions in stability. So the first one is that, well, if you are able to scale this V to 0 by elements of G in the limit, right, so this is a closure, then this V is unstable. Okay? So that's that will be bad, we'll see, as the name suggests. Then semi-stable means that, okay, it's the opposite. Okay, so then you cannot find 0 in the orbit closure. B is polystable if it's semi-stable and the orbit is already closed. And the best case is stable when you have polystability and also the stabilizer, right? So all the G's that fix the little v, this is finite. Okay? So these are, okay, you can have this point and you can classify it depending on its stability. And in particular, we're going to also define the null cone of the action by G by the set of unstable vectors. And then the problem, the capacity problem is, well, find the infimum along the orbit of these norms of a particular V. And the observation here is then the capacity is 0 if and only if V lies in the null cone. So there is another definition of null cone that's more algebraic in terms of, you know, like what Hilbert was thinking in terms of invariance. But here we're going to use this definition. Okay, so now that we have the stability notions, then let's go back to how this connects to maximum likelihood. This will be our first example. So this is just recalling the definition of log linear model. For some technical reasons, we're going to assume that the 1, 1, 1, 1 is in the row span of A. In particular, this means that the uniform distribution is always part of the model, which is something nice to have. That's the maximum entropy when you don't know anything. You just say, well, a uniform distribution. So this is the example is independence model. There are other models called hierarchical models and other graphical models that I will get to later. These all fall here. And there is actually a nice geometric interpretation already, just in geometry level, of when the MLE will exist. And that is, well, this A has columns, and you can consider the convex hull of these columns in this set D space. That will be a polytope. And okay, if you like polytopes, automatically then you have access, you know, to all these things. And in particular, well, it turns out that what you need to do to know if the MLE will exist is you take your U, right? Remember the U is the vector of counts. And U bar is the normalized, the empirical distribution. You compute AU bar, and then you see whether this lies in the relative interior of this polytope or not. So if it lies in the relative interior, the MLE is going to exist, and otherwise it will not exist. And so this is some characterization. I put here some names, people who have worked with this characterization. And yeah, so this is very nice. And this is gonna help us now relate to the invariant theory. So what's the group here? The group is gonna be the torus. And so consider a complex diagonal invertible D by D matrices. And the action is going to be given by the natural action. We're going to have another vector B that's going to serve as modifying the action a bit. This is what we will call a linearization. And so how do we act? Okay, so we have this lambda, and we just multiply by the diagonal matrix, lambda raised to each of the columns of A in each of the coordinates. And so this is this shorthand notation for, you know, the monomial. Everything is, you know, vector raised to vector, so it's this usual notation. If you're not familiar with it, I have an example here. So let's say this is the matrix A. Let's say B equals 0. And so what you're doing, this action is really just multiplying. Here you can see lambda 1 squared because this is 2, 0. When you have 1, 1, you have lambda 1 times lambda 2. And when you have 0, 2, then you get lambda 2 squared.
So what is the rule of B? I don't get it.
Oh, yeah, so the B will modify here the action. It will come in the theorem. So that's why we need it. I'll show you in the next theorem. So it turns out this is like the main theorem in this case, the first main theorem, I would say. So consider this U, vector of counts, and the sample size, A, our matrix that defines the log linear model, and B is going to be this A times U, which is going to be my, what we call sufficient statistic, but so it's that this matrix A applied to the vector of counts. And so then the MLE exists if and only if the all ones vector is polystable under the action of this torus given by the matrix n times A with linearization B. So this B is coming here into this linearization. And well, I want to give an idea of, so the proof is really using, so relying on a Hilbert-Mumford criterion to establish an equivalence between the support of vectors and how like the stability relates to belonging to the polytope that they define. So namely, you take a vector x, and then you're going to take this polytope that corresponds to taking the convex combination, so the convex hull, of only the ones that have support in x. Right? So you're taking these sub-polytopes, and you're looking at these sub-polytopes, and then the question is, well, the stability is completely determined by this B lying, where does it lie with respect to this polytope? So in particular, you will be unstable if and only if you're not part of the polytope. You will be stable or semi-stable if you are in the polytope. But here is where we make the distinction. If you are in the relative interior, then you're polystable. If you are in the actual interior, then you are stable. And so this dictionary is what basically is behind this, because so this vector of all ones is going to have full support. And okay, so this is the case, the nice case, so we can start to see what's the message will be that stability is going to be good for ML estimation. Yes?
So having the vector of all ones, that means that you lie on some affine hyperplane. But you're taking the linear span of that, I guess, not the affine span. Is that?
Yeah, this is linear, yes, linear span, yes. Okay. Yeah, exactly. So
But the convex hull, if it lies on an affine hyperplane, the convex hull is not going to be full dimensional.
Right.
So how are you going to get something that's in the interior? I mean, you only have a relative interior. It's not full dimensional.
Yes.
The last, I mean, it has no interior if it lies on an affine hyperplane.
Yes. So I think this. So yeah, in that case, then this will not be possible.
But your assumption was that A has an all ones vector in its row span, which means it lies on an affine hyperplane.
Yes. Okay. Yeah, that is true. So yeah. So we actually don't get that case.
Okay. I guess your result is polystable.
Yes, exactly. It's about polystability.
Okay.
So it's either polystable or it will not be. There will not be an element. Yes.
Is unstable also not possible then? So if you're assuming that U is non-negative?
Yes, exactly.
Yeah.
So if U is not negative, then you also won't be in the unstable.
Mm-hmm.
Then you can only be semi-stable or polystable.
Right, because the polytope is the image.
Yes.
Simplex under the.
Exactly. So yes. So actually, I mean, okay, yeah. In this particular linear case, we don't get the full 4 cases. We don't observe everything. But I guess the message is there appears to be that having stability, or at least polystable, will be good for the MLE because then this will exist. And otherwise, in this case, being semi-stable will mean that it will not exist. So, okay, this is the discrete case, and we already see something happening. I want to move on to the Gaussian case, that then more things can happen in these 4 cases. So, what is the Gaussian? So this is just a reminder, the multivariate Gaussian density looks like this. There are 2 parameters, mu and sigma. Mu is the mean parameter, sigma is the covariance matrix, which has to be symmetric, positive, definite. And so now, well, we cannot think of the density itself as lying in some, I mean, that's not going to be our parameter space as before. But now we just restrict to this, in this case, actually we restrict to some subset of means and covariance matrices. So then the algebra and geometry is going to come directly here in the parameter space. Okay, not at the level of the density. And so, okay, one example, let's consider this Gaussian Markov chain, which is also a graphical model that we'll talk at the end. So, okay, in a Markov chain, Markov property, you remember, tells you that, well, if you're in the present, so the future, like, only depends, okay, what's it called? Condition on the present, the past and the future are going to be independent, right? So, to try to guess what's going to happen in the future, free, and you have 1 and 2, you only actually care about 2. So another way of saying this is that 1 is independent of 3 given 2. And well, what does that mean in terms of the parameters? It turns out this is a very nice condition in the inverse of the covariance matrix. Namely, the inverse, the entry 1, 3 in the inverse must be 0 whenever this happens. So it's an if and only if. And so then the model will be all matrices sigma, 3 by 3, that satisfy that the inverse entry 1, 3 is 0, which translates to this, right? So this is a particular minor that has to vanish in sigma. And so this will be a 5-dimensional model then, right? And so the models are going to look like this. And this is a nice example. Okay. So now we can do the same idea. We're going to do maximum likelihood estimation. So we're going to identify the model actually, just for convenience. We're going to think of concentration matrices, which are these inverses. So that means that in this case, if I think of it as a concentration model, this is going to be a linear model because the condition is just that 1 entry is 0. So we're going to look at that. The model is going to be concentration matrices. And we're going to have data. This is going to be multivariate data. And now we want to have what's the analog of this U. Remember we had this U, and then the AU, which was the sufficient statistic. Well, the analog is now the sample covariance matrix. It's going to look like this. Just taking, so this is going to be a matrix, right? So these are rank 1 matrices, and then, oh, I'm actually missing a sum here. Guess it's kind of, what is it called? Einstein notation or something. No, okay, I missed a sum here, okay? I meant the sum I want to add. Okay, and then, okay, the log likelihood, it turns out you can write it in this way. You can see it's not so hard to see from the density here. You're gonna get a nice quadratic form coming down, and then you got this log det of sigma, and then yeah. So then this is the normalizing constant. This is the log det of the sigma inverse, which is psi, and here there is just a trace trick. It's called the trace trick, right? Where you rewrite this as the trace of this because it's a scalar, and then you can put the x minus q transpose on the other side by using simplicity of the trace. And then you can get the sum of the x minus mu's, and then you get the s. So that's how this trace of s appears here. I'm skipping the details. This is a good exercise. And so, okay, once you have this, what are the models that we're going to be interested in? Well, these will be Gaussian group models. So we're going to now have a group that is a subset of GLM. And we're going to consider concentration matrices that can be written as G transpose G, where G is in this group G. And so if we want to find out the maximum likelihood estimate, we need to maximize this function, and it will turn out it looks like this. So now we're going to have, the interesting thing here is that now, but once you replace this size by G transpose G, you'll be able to write this as some norm. And now you should start thinking about the capacity problem, because now maximizing this will be, in one step you want to somehow, well, minimize this norm here. Of course, there is still this part, but it turns out that you can do this in 2 steps. You can find the one that minimizes the capacity of this y, and then you can find the correct scaling. So let me, here this will be, it's clear in this equation here. Yes, so these are these y's, as I said. In principle, the y's, of course, are in Rm, but you can replace this by Cm to make things nicer. Here now, this infimum is going to be over SLM, and then you're going to find this tau is going to be the right scaling so that you find your optimizer.
May I ask?
Yes, of course.
So this idea of taking this Gaussian model of a group, does it appear in naturally, or is it some kind of a very abstract construction, or did you model it after some cases of interest?
So, okay, I will say yes. Okay, so I mean, these Gaussian group models do come from specific models that have been used in statistics. One critical example is the matrix normal model, and that's actually how we started looking into it. So we had developed the theory for matrix normal models, and then realized that we can be generalized to any Gaussian group model. And I'm going to give, towards the end, I'm going to give examples of these that had to do with graphical models, and these are used a lot. Yeah, thank you for the question. Okay, so I'm gonna already tell you what's the main, okay, so this just shows that, okay, you can have the MLEs, and if there are multiple ones, you can actually find all of them via a stabilizer of under the group. And let me show you the main theorem here. And so, okay, one needs some hypothesis. In this case, we have linearly reductive. And now we really have the four possibilities. So, if your y that you observe is unstable, the likelihood is not going to be even bounded. So in particular, of course, the MLE doesn't exist, but it's because the likelihood is not even bounded from above. If you have semi-stability, you at least guarantee that the likelihood will be bounded from above. But still, the MLE may not exist. For that, you need to go to polystability. And finally, the best case is when you have stability, because then you can show that finitely many MLEs will exist. And this, in this particular case, you will show that this is equivalent to being a unique MLE. And then, so now this is really the full dictionary that's relating very nicely, I would say, the conditions on the likelihood, which is this maximum likelihood estimation problem, to the kind of stability from your data.
So is that something like the group acts freely when you have finally made AMLEs? Right, so
This part.
Yeah, because like a point on the model that could be over-parameterized.
Yes. Yes. And this may fail if we relax some things. So here I have two other versions of this. So let me see. Yeah, so this version where we're over R, GLMR, then, for example, here we lose this equivalence. So there could be finally many MLEs, but then doesn't mean necessarily stable. It will be polystable. And these are examples that independence model we talked about. A matrix normal model I mentioned, didn't define it, but they all fall into this case. And there is another one where we drop the condition of being linearly reductive, and then we only have one implication here, why polystable implies MLE exists. And you can see here now the group changes a little bit. We have this plus minus, that means we look at determinant 1 and determinant minus 1 as well. So there are different variants that you can play with. And I think, well, Anna will know that like the latest when one can generalize even more. Yes?
Could you recall what's the space on which the group acts?
So these just are M.
This is RM.
So yeah, we have this, sorry, well, not RM, I guess M times N. So I'm thinking of matrices, basically. I'm thinking of the data, I just look at it as columns, and yeah, I'm gonna act.
And you actually have the rows of that.
On the rows, or the columns, depends. I guess, no, okay, this is M, yeah, YI is in RM, right? So I have,
Thanks.
yeah, no, thank you. So that's how we're gonna be acting. And I think this should come, okay. There's Gaussian group graphical models, which will be our key example.
And where does this condition that it's closed under non-zero scalar multiple
Ah.
come in?
Yes, this is a good question. So basically, yeah, so we need that when we're acting here, so we need that if you have a point in your model, then any multiple of it is also in the model. This is not a crazy requirement because, so this happens if you have this your data, that means that if you scale it, let's say you scale your data, then the resulting covariance matrix will again appear in your model. So yes, so this is some condition that we need, and it's natural from the statistics point of view as well. But I guess in principle you could have models that don't satisfy this, and then this wouldn't work. So yeah, we didn't really explore that case, I guess. Yeah. So okay, let's talk about these graphical models that I've been advertising. So, well, these are some. Yes. Yes.
So having a compact group, does it make sense then?
Well, these are linear algebraic groups. So,
But they're not closed under the scalar multiplication.
well, like, yeah, the cyclic group is not, for instance. But that condition was where it's not necessarily linearly reductive. Yeah, so reductive.
I'm not sure.
Yeah. So
I'm not sure you answered my question, and I was asking the speaker actually.
No, it's fine. I'm happy if Frank answers the questions. Okay. All right. So I was not thinking.
actually, I think, I mean, when you have a group it can have many real versions. There's the split form, which is typically non-compact, like SLR, but there's also the non-split form, which is compact. Does that say anything about an actual with the non-split form? I think that's.
I wouldn't know. Oh no, Anna, do you know? This makes a difference.
I mean, we saw in some cases regarding compact groups that, remember we had that the maximal compact group leaves the MLE unchanged.
Because of the campness stuff.
Right, yeah, exactly. So then such models degenerate
interesting.
from the MLE perspective. Yeah, exactly, because you only care about the norm.
Thanks.
But I guess even if it wasn't like that, you'd have like a compact orbit, and
Then within the orbit, you can.
you have a compact group.
Okay. Well, I think there is something interesting to discuss. And yeah, so okay, so Gaussian graphical models, just like a quick summary would be, you have a graph, which now this is like fancy G, because I don't want to confuse with the group. And so this graph, it's a DAG, so it's directed acyclic graph, has m nodes, and the idea is that each node represents one variable. And then the edges encode conditional dependence between the variables. So then the nicest case is just think that if you have an edge from j to I, xj is a cos of xi. Okay, and let me introduce this notation, a parents, right? So if you have a node I, the set of all j's that point to I is the parents. And well, then this is an example. And then we're gonna add some coefficients here to each edge. And then the one of the classical cases is when you have a linear model, which means that each node is a linear combination of its parents up to some error. And this error usually taken to be Gaussian. And so these lambda ij's are called the edge coefficients, and this, then this is the equation for each xi. So you think about this, a bunch of linear regressions, where each x4 in this case would be then a linear combination of x2 and x3 up to some error. Okay, so you can write this in some nice form, vector form, x equals lambda x plus epsilon, where lambda is the matrix of weights, where there will be 0 whenever there is no edge. And the epsilon is this Gaussian error that's usually taken to be diagonal, which means that the errors are uncorrelated, but there's also a version where you can do that errors are correlated. I will not talk about that one. And okay, so in this setup, you can see that the covariance matrix, so from this representation, you can solve for x like this, just identity minus lambda inverse times epsilon. You may wonder, well, I minus lambda is always invertible because this is going to be, you can make it so that it's a triangular matrix with everything once in the diagonal. And yeah, so then the covariance looks going to look like this. And this goes suspiciously, looks like these Gaussian group models that I was defining before. And indeed, if we consider all g's that have zeros whenever there is no edge from j to I, then this GG forms a group if the G, the graph G, is transitive. And so this is what that's called a TDAG. And TDAG is what you would expect. So if there is an edge between K and J and another edge between J and I, then you know that there's going to be an edge from K to I. And so in this case, then you can show that then, well, then the model is actually this Gaussian group model by this particular group. So, okay, so in this case, we can start saying nice things. So this is one example. This TDAG, you can see it's a TDAG. And, well, it will consist of invertible matrices where there will be 0. Here, for example, this means that there is no edge between 1 and 2, or 2 and 1. And then here, there is no edge between 1 and 3, so this 3, 1 is 0. And there is no edge to 2 to 3, so the 3, 2 is 0. Okay? One needs to be careful, these are not symmetric. And okay, so then this is the group. And then the Gaussian graphical model turns out to be, have this psi 1, 2, psi 2, 1 is 0, which means, again, a 0 in the inverse. So this will be, in a sense, is actually equivalent to, well, similar to the one that we had with the Gaussian Markov chain. All right, so how can we use this theorem that I showed you on the equivalence for this particular case? Well, in particular, it will tell us if you observe this matrix Y, I was thinking as a matrix, so like just look at the samples and just put them together in an n by n matrix. You can read if the MLE will exist or not, depending on the stability. And in particular, well, if you can find a row that is the linear span of the rows corresponding to its parents, then it's going to be unstable. And then the likelihood will be unbounded. Remember, that was the main theorem. And otherwise, this is going to be polystable. And in which case, then the MLE exists. And so this is an example. So I can give you the same graph that we had. Consider this, these are two samples, so I have two columns. So this means that I observe for this variable, I observe a 1. For variable 2, I observe a 0. For variable 3, I observe a 2. And then I sample again, and I observe 2, 1, 4. Okay? Another question is, okay, can you find an MLE for the covariance matrix that lies in the model like this? And well, if we believe this, right? So then we see the question is, can we find a row that is a linear span of other rows? Well, in this case, indeed, 2, 4, you can see it's a linear span of 1, 2. And so this is going to be an unstable case. So then we know that MLE doesn't exist. And in this case, well, nothing like that happens, and that's polystable. And in that case, the MLE will exist. And the null cone, in this case, you can find it easily to be given by these two components corresponding to the minors, the corresponding minors. Here you can see these 2 by 2 minors appearing. And in particular, I will say that it's Zariski closed. And this is interesting because, I'll show you the next example, it's not always Zariski closed. So look at this now that changed the model. Instead of the arrows looking like this, they go now both into 3. This is what we call a collider. So the Zariski closure is going to be varieties of the variety of matrices of rank at most 2, but you could have points that are in the null component Zariski closure. So this would be a typical example where, well, this matrix has rank 2, but the third row cannot be written as a linear combination of the first 2 rows. And so that means that the MLE actually will exist, even though it's this kind of degenerate case. And, well, we can ask, okay, what is the MLE? We can use the techniques that I was showing you, like trying to find the minimal norm in its orbit. And you can find this will be the identity. Then you need to scale it. This is going to be 2 times the identity. And this will have a stabilizer, non-trivial stabilizer. And therefore, you can find there will be infinitely many MLEs in this case. So it's one of these, like special cases.
Sorry
Yes?
to interrupt. But is the group the same in the 2 cases?
The group is, well, it's not the same. It's not the same.
And so one, okay, I guess.
Because, in here, the group is defined by these missing edges. And so, it will change a bit, but
But so if a group is reductive, it will always be Zariski closed, no? Or am I wrong?
If it's reductive, yeah, I think that's true. But in this case, it doesn't need to be.
But the group wasn't reductive.
Exactly, it doesn't need to be reductive.
In the
For now,
previous
you want to do it was upper triangle. No, it is.
In one of the examples,
triangular.
it is.
It was the upper triangle missing one.
Like, it's this example here, I guess,
Is
right?
that-
This one.
It's a triangle.
Is it reductive?
I guess this one, yeah, this one is. I think it's. But this one for sure not. This
But
one
isn't
for
that just the transpose of the other ones? You reverse the arrows?
That's a good point. Yeah, just reverse the
The
arrows.
adjacency matrix, which is
I
upper
just
triangle,
reversed.
is just the transpose.
Yeah, that's true.
So it's the same. It's isomorphic.
Okay, yeah. Okay, so it's not the same group, but it's isomorphic. Okay, then it cannot be linearly reductive. Then it cannot be reductive. The first one. Yeah, because I think, yeah, I think your point is true. Like, if you knew that it's reductive, then it would be always Zariski closed. I think there is a theorem like that. And so the question is, which TDACs have Zariski closed null cones? And well, it turns out the answer is if and only if the matrix G has no unshielded colliders. And what do I mean by that? This is an example of precisely the unshielded collider. So this is not. And unshielded is called because if there were an edge here between 1 and 2, then we wouldn't call it an unshielded collider. It would be a shielded collider. So an unshielded collider is a subgraph like this, where there's no edge between the 2 parents. Okay. In graphical models, sometimes people call this the not. If you have this, would be a moral graph. Otherwise, this is an immoral graph. It's about like the parents being married or not. That's the okay. But we don't use that terminology here. It's just okay. You have an unshielded collider or not, and so this very interesting condition. Because it's known that if a graph has no unshielded colliders, this DAC has no unshielded colliders, then if you remove the direction of the edges and just look at the undirected graph, the graphical model associated to that is symmetric. That's when you just make everything symmetric. Whenever there is no edge, you put a 0. And well, those are again also a study and well understood. And one natural question is, well, if I have a directed graph and I remove the directions, do I change the model or not? Well, the answer is if and only if you don't find this kind of thing. So in this case, this will be an example where this is equivalent to just having undirected, and this is equivalent to just having flipping the arrow here, 1 to 3, 3 to 2, which was the first example I gave with the Markov chain. So it turns out that all those models are equivalent, but they're different from this one. This one is different. Okay, so there are more things that one can do. A very interesting question is, what is the minimum number of samples that one needs so that the MLE exists with probability 1? This is called the maximum likelihood threshold of a model. And it's non-trivial to answer this in general. And for graphical models, this is very interesting because, so normally, if you have a full model, you need as many samples as the dimension in order for the MLE to exist. But the nice thing about graphical models is that you actually need fewer in practice, fewer samples, which is good because in practice you may deal with high-dimensional models and not a lot of data. So you want your MLE to exist even if you only have a few samples.
Yeah, this is like a Carathéodory number for compact sets.
I guess so, yeah, some kind of. So this is an interesting problem. And now, knowing the relationship to invariant theory, then one can translate this to, okay, how many points do I need? What's the rank of this matrix so that I will have some stability, that I can guarantee some stability. And so that's what we did for matrix normal models. We actually found some new bounds. So they were previously studied by Matthias Durton and collaborators. And then we found some new bounds. And not much later, Harm Dirksen and Visu Makam used our result, this equivalence, to give a closed form formula for these matrix normal models that has to do with GCDs of the dimensions. And so this was really nice. We were really happy that this equivalence helped. That this was using now completely geometric invariant theory to solve a problem in statistics. And so this is the recap. There are other consequences that you can do. So now you can see, so this is SY with the MLE and the invariant theory side. You can think about algorithms, right? Of course. So in statistics, we have algorithms to find the MLE. There are, for example, this iterative proportional scaling in the discrete case, IPS. In this Gaussian case, there is something called the flip-flop algorithm. And, well, people have been studying here, right? Ways to compute, solve the capacity problem. And here I have a reference with Peter Burgesser, collaborators, so Avi Victorson here. And you can see they have some complexity analysis on how good one can actually find certificates for the null cone membership problem, right? Where just one asks, do you want, can you guarantee, can you give me some evidence that this belongs to the null cone or not? And this can be done in there are some polynomial time guarantees. And this means that we can translate this to statistics and talk about ways to know whether the MLE would exist or not. And so to conclude, so this was just an example. My main message is that there is deep algebra and geometry that you can find behind statistical problems, and many things come in: discrete geometry, combinatorics, optimization, and in particular, I told you about the bridge between invariant theory and ML estimation, and this is the takeaway, I would say. So if you remember something from the talk, is this: these stability notions, which is unstable, likelihood unbounded. If you're semi-stable, now you have a bounded likelihood. Polystable, now you got guaranteed existence of the MLE. And stable is that best case where MLE exists uniquely. And with that, I thank you for your attention.
Are there more questions for Carlos?
Yes?
When you have this, that there's like finitely many MLEs, then you can conclude that it's unique. Could it be that there are many different critical points within the the positive definite cone, but one of them is a maximizer, or is it convex? Like, how do you get the uniqueness?
Yeah, there could be several critical points, but only one of them is a maximizer. Yeah, so the ML degree doesn't need to be 1 necessarily.
And it doesn't need any genericity on why, that maybe there are two maxima and they actually have the same value on the likelihood.
I think for finitely many, I don't think this is possible. You can have this infinitely many, like the example I gave, but at least for these nice Gaussian group models, this cannot happen. For other models, in principle, yes. You just say if you don't have something generic, then for sure.
So you went from directed acyclic graphs to these strong results you got for transitive directed acyclic graphs. You can, of course, take the transitive closure of such a graph. It must give a very different model then, I suppose, this is why you're working.
Yes. Yeah, if you take the transitive, then I guess, so you are...
I mean, you're just adding more...
You're adding more
inputs.
edges, right? So you're adding... you're removing some zeros, right? So you get a super model of the original. Yeah, I guess you could...
I guess there's more edge parameters, but still, like if you have a variable here and it goes 2 steps, it's affecting this one through the intermediate steps that you're adding more direct. But it's okay.
Yes, I mean, I guess you could.
I guess it's richer.
I mean, it makes sense from the point of view if you think about flow, right? They're just on networks, right? They're called Bayesian networks. In the end, it makes sense to take this kind of transitive closures so that really, I mean, okay, if you affect something even down along the way, then you're still affecting it. But yeah, I think there is some kind of generalization that Philipp and Anna were pushing at some point for not necessarily having a TDAG. Now, if you want to maybe comment.
Yeah, so if your graph is not transitive, then your G is no longer a group, but you can still define the set G, and then you can still say what you think it unstable, semi-stable, polystable, and stable are, but now they don't refer to a group, they just refer to a set of matrices. But then with respect to that definition, which is then no longer in relation to any group, but then you still have this correspondence.
That would be the extension.
So in geometric invariant theory, for the unstable case, you have this optimal one parameter subgroup. That also tells you if you run this gradient flow of the function you're optimizing, it will tell you like the direction it approaches at infinity somehow. I wonder, is there any significance to this or any usefulness for this in statistics of the unstable case?
I think that's a great question. I don't know. It would be good to figure that out. I don't know, like, yeah, I don't know. It gives you some kind of optimal direction to.
There's something.
I don't know. Maybe they could tell you, how to modify the data such that. Yeah, I don't know. This is an interesting question.
So, if I've understood correctly, all these notions on the right-hand side assume that you are living in an affine space.
I'm not sure what you mean by affine space, but yeah. Yes.
Are there versions of this where you work over projective space? For instance, in your example of the coins, where you had there for me was a quadratic, like a projective quadratic.
In a sense, we are in projective space. I mean, I guess related to the hypothesis that was asked tonight. So we do assume that if you have a point in the model, then it's closed under scalar multiples. So I feel like this is, in a sense, this projective space is there. What you can also do, I mean, what is interesting, I mean, it came up a bit, but like Rm versus Cm. So that's also interesting. You look at complex numbers versus real numbers. Because as you know, so the geometric invariant theory can change. And this is also reflected in the statistics.
Okay, let's thank Carlos one more time.
Thank you.